Hello, my name is Aaron Meek. Today, we're going to be discussing this logical circuit and what happens when you negate its input and you negate its output signals. And it's my job to demonstrate to you and show why these are not only not equivalent, but they're not even opposite of each other, and that they are fundamentally different logic circuits. So we're going to start with an OR gate and an AND gate. And what's happening here is that I have four signals total, but two signals are going into my AND gate, 1 and 2, and the output is going to a non-inverting output. So these are all non-inverting inputs, and for the OR gate, it's going to be a non-inverting output, which is right there. And for the NAND gate, again, we have two non-inverting inputs, because we want to treat it as an AND gate instead of a NAND gate for our test, just to ensure that all of these work. I'm going to invert the output of the NAND gate, which will just turn it into an AND gate. And so this is going to be the basis of understanding what's happening on the larger scale when we get back to that circuit. So let's focus on the OR gate. And what we can see here is that any time I turn on one of the inputs of 1 and 2 to the OR gate, or I turn on both inputs, we get an output high, right? So anytime the input is high, the output is high, or both inputs high. Let's talk about the NAND gate with an inverted output. And so it's treated like an AND gate, and we can see here that both inputs need to be high in order for the output to be high. Okay, but what happens when we invert both the inputs and the outputs of these logical elements? So we can see here on the breadboard that nothing has changed, and the OR gate is still being treated as an OR gate, and the AND gate still as an AND gate. But what we've done is we've swapped the non-inverting inputs to inverting inputs, and we've also swapped the outputs respectively for the OR gate and AND gate. And so now we're going to test what happens to these logical elements when we swap the inputs and the outputs. First, we focus on the OR gate. When you flip its inputs and its output, what you get is an AND gate. You can see that as I push these buttons down, the only time the output is high is when I provide a signal to both the inputs, a high signal to both the inputs. Because they're inverted and the output is inverted, we get an AND gate. Now with the AND gate, where the signals are flipped and the output is flipped, we get an OR gate. And so anytime I provide any high signal, or both high signals to its inputs, we get a high output. Now that we fundamentally understand what happens when we negate the inputs and the outputs, let's talk about our first circuit. So over here, we have inputs A and B going into a NAND gate, and so the output on that line will be not A and B. Same thing with C and D. We get not C and D. Those get fed into our OR gate, and so we get not A and B, or not C and D. Using de Morgan's law, we can get not A, or not B, or not C, or not D as the output, and that is what we will find in the table. So looking at the table of this first circuit, we're assuming non-inverting inputs and non-inverting outputs. So when we set up the whole system, we have our NAND gates, and we have our OR gates, and we have all our signals hooked up. Signals 1, 2, 3, and 4. Those are fed in to, the outputs of those are fed into the OR gate, and then the output of the OR gate is fed into our non-inverting output. So inputs are not inverted, outputs are not inverted. And we can see that this system, with inputs low or individual inputs high, we get an output high. Flipping through all the combinations shows us that all the outputs are high. until we actually set all input signals to high. And so, for non-inverting inputs and a non-inverting output, we show that the only case where the output is low is when all signals are high. Now let's talk about what happens when you do invert both the inputs and the outputs. And this is the logical diagram that we get when we do so. Taking a look at the diagram a little closer, we see that we still have our A, B, C, and D inputs, but now they are all negated individually. We can also see that the output is also negated. And so when we feed A and B into the first AND gate, we actually get not A and not B. And because it's a NAND gate, we get a negation of all of that. So using De Morgan's law, it actually turns into an OR gate. And the similar thing happens to C and D because they're actually logically the same setup. So we get not C and not D all negated. And using De Morgan's law, we see that it actually is just an OR gate on C and D inputs. We feed both of those into the NOR gate. Now is acting as a NOR gate because the output is negated. So we're feeding it A plus B plus C plus D. And then we negate that and we get the negation of all of A or B or C or D. So that's what we should expect. And taking a look at the table, we can see that the only case where we get a high output is when all inputs are low. So now we have our setup. It's the same setup on the breadboard side, but now we've inverted both the inputs and the output. So these are all inverting inputs and outputs. And going through the system, we see that this was very difficult to do with one hand, and so I'm cycling through most of the possible inputs, but I have confirmed with both hands that it does match the table, and the only state where the system outputs a high is when all inputs are low, which agrees with our truth table. Now let's compare these two truth tables side by side and demonstrating that they are in fact the same outputs that we see based off of the inputs that I've demonstrated physically through these setups. Take a close look at their respective outputs. For the first circuit is table 8, the second circuit is table 9, and we can see that just by looking at the first two configurations where we have no high inputs, both tables produce a 1. That means that these are not the negation of each other. And the second state, where only D is high, we see that the first circuit produces a high output, while the second circuit produces a low output. And so not only are these not opposite, but they are fundamentally different logical setups. And now we've come to the end of the video. Hopefully I've demonstrated to all of you how, not just the case, but how that by inverting the inputs and the output for a logical configuration does not provide you with the same logical configuration, and in fact, fundamentally will produce logical inequivalencies. And so it may seem intuitive at first that by feeding an input, negating it, and then getting the output and negating that you've done nothing to the system, but because there are a lot of layers and interesting ways that these layers interact with each other. For example, negating the inputs and the output of an OR gate produced an AND gate, negating the inputs and the output of a NAND gate, or an AND gate rather, produced an OR gate. And that was demonstrated at the beginning of this video to show you that not only will it not produce the same thing, the same output, but it actually won't even produce the opposite output. They are fundamentally different logical configurations. Thank you.